Question number 1 is asking us to find the time taken for the metal plate on a steam iron to reach a working temperature of 125 degrees, and it starts at 20 degrees. So since this is about heat energy and changing of temperature, we know we're going to use the equation E equals mc delta theta. So since it's the object of interest, the metal plate, we need to write values to do with the metal plate. They've told us the mass of the plate is 1.2 kilograms. The specific heat capacity is 450 joules per kilogram per Kelvin, and the change in temperature must go from 125 minus 20, so from 20 degrees to 125. In the energy input, since it's electrical energy here and they've given us the power of the iron, we know energy is power times time, where this power is 2.1 times 10 to the 3 watts. So T should be equal to mc delta theta, all divided by P. When you put those numbers in, you should get 27 seconds to two significant figures. This next question, there's a few different ways to approach this and answer it. First of all, understanding the object of interest now is this water turning into steam. So we're thinking about all the energy changes that are taking place for the water, which starts at 20 degrees, ends up being heated to 100 degrees and then boiling and turning into steam. And the claim is 60 grams per minute is what this can be generated by this iron. So what that means is this is a rate of mass, so therefore from grams per minute, I know this is the same as m over t as an equation, and that's 60 grams per minute. So I won't worry too much about the units at the moment. Normally we use kilograms and seconds, so I could turn this into kilograms per second, but I'll leave it at 60 grams per minute. What I'm interested in is this part of what that means, mass over time. So thinking about the energy transfers that are taking place, heat input from the iron, which it says it's maintaining working temperature. We know heat energy is power times time from the previous question. That is converted to raise the temperature of the water, so heat to raise temp, and we know that the equation for that is mc delta theta, and this is all for the water. And then when it does raise the temperature to 100, any energy going in will then turn that water into steam, so that's the heat to change state. And we know from the equations that's ml. So I could put this into an equation now and try and get this m over t as the subject. So this is what it's going to look like. So pt equals mc delta theta plus ml. I'll divide by t, so p equals mc delta theta plus ml, all divided by t. I could factorize out m over t to get p equals m over t c delta theta plus ml, okay, because I want this m over t as a subject. And then finally just rearrange that and you get m over t equals p over c delta theta plus ml. When you put these numbers in the calculator, making sure we use the correct values, they've given us the specific heat capacity of the water to be 4,200. They've given us the specific latent heat, L, in the equations to be 2.3 times 10 to the 6. Delta theta, well, we know the water starts at 20, and if it needs to reach the boiling point, it goes to 100. So delta theta must be 80 degrees. So those are the values we want to put in. Power, as before, is that what the heater is providing, which is 2.1 times 10 to the 3 watts. So when you put these numbers in, you get 7.0 times 10 to the minus 4 kilograms per second, because all these units are the standard units. I mean, mass must be in kilogram, time in seconds. So all I have to do now is just compare that with the 60 grams per minute. So I should convert this into grams per minute. So I will times it by 1,000 first to get into grams per second. So when I do that, I get 0.8 grams per second, and then I'll times it by 60 to get into grams per minute, and I get 48 grams per minute. So claim is not true. Okay, that's less than the 60 grams per minute it claimed. The first part of question 2, we need to state 2 assumptions of the kinetic theory. Now, a good way to remember all the assumption is this acronym, RAVED. And obviously we only need to state 2 here, but RAVED is a good way to remember all of them. So R stands for that the particles move in random directions. So the motion is random. A refers to attraction, but the point being that there is no attraction between the molecules, so no forces between the particles. Okay. V is to do volume. Volume of particles, negligible. Compared to gas volume. E refers to elastic collisions between the molecules, so kinetic energy is conserved. And then D refers to the duration of collisions is short compared to between collisions. Okay. So any one of these 2 should get you the 2 marks for that. The second part of this question, explain why molecules of a gas exert force on the walls of the container, and we have to refer to Newton's laws of motions in the answer. So there is a format you can follow here. Starting off with Newton's third law, you could refer to what are the 2 objects of interest. In third law, if you remember, there are 2 bodies, and each body applies a force on the other body of the same type in the opposite direction. So we could start by saying particles exert force on wall, and according to Newton's third law, the wall must apply a force on particle in opposite direction. Okay. Now let's think about what happens at that point. Okay, and we need to try and bring in Newton's first and second law. So we could say that the collision at the wall, particles will change direction, and hence velocity, because if there's a change in direction, there is a change in velocity. According to Newton's first law, if net force equals 0, there is constant velocity. So therefore, just because there is a change in velocity, Newton's second law states a net force causes a change in velocity divided by time. Okay. And that should be enough, referring all 3 laws to say why there is a force on those particles due to the collision on the wall. This calculation question here, we are given some information about this gas. I'm just going to list out some of the values to keep track. We've got volume is 0.35 meter cubed. We've got the pressure of the gas to be 220 times 10 to the power 3 pascals. And they've given us the kinetic energy of one of the molecules. So this is the kinetic energy of one of the molecules. And we want to work out the amount of gas in moles. So the equation we might need to use here, that involves pressure, volume, moles, will be PV equals nRT, where R is just a constant, 8.31, you could get from your data sheet. V we were given as 0.35, P is 220 times 10 to the 3. So what it looks like we're missing is temperature. So clearly the other piece of information must come from kinetic energy. And if you look at the formula sheet, kinetic energy of a gas molecule can be found from temperature with this equation, 3/2 kT. Rearranging this equation to get temperature, and you should find temperature is 324 Kelvin. So now we have a value for temperature of 324 Kelvin. We could rearrange this equation, PV over RT, to get 29 moles to two significant figures. The final question, we are asked to draw a line for this same gas, which is a fixed mass of an ideal gas, so we're talking about the number of particles doesn't change. Looking at this equation again, we see that the change that they've made is that temperature has been doubled. So looking at this relationship, PV is proportional to T, since N and R are constant, and if you double this, then something here has to double, okay, for this to be true, right? So you can think of it as for every pressure, okay, V is double. So I can look at my scale and see, well, what can I do with these numbers? So if I start from the top, for the largest pressure here, up here, the volume could just say an arbitrary number of 1. And let's just list out these numbers to keep track. So if the volume here is 1, I have to double the volume. That means the new volume would be here for that pressure. Let's look at another one. So this pressure here, the volume is 2. I double that and I get to 4. Let's look at another one. The volume here is 4. I double that and I get to 8. So it's really just a curved line going through these points. Oh, alright, yeah, obviously, I haven't gone through that point properly, but you get the idea. It just needs to go through these points, and that will be for the 2 marks. First part of question 3, quite unusual question really, I think. It's asking you to state and explain the location of the excess electrons when charging up a sphere. So if you've ever used a Van de Graaff generator, large sphere that you charge up, the electrons are on the surface and also spaced apart. Since they repel, electrons being negatively charged. Next question, we have this graph that's given to us, and you can see on the axis we have a V on the y-axis, R on the x-axis. Okay, so this is potential and distance, and they've shown us this curve. For the first part of this question, it's asking us to find the magnitude of the field strength, and they've even told us here how to get that. So it's a change in V, in other words, change in what's on the y-axis, divided by the change in what's on the x-axis. So change in y, change in x is just gradient. Okay, so we need to find gradient at that particular distance that we're interested in, as 0.3 meters. Okay, so looking back at the graph, you see it's a curved line, so you need to, with any gradients of a curved line, you need to draw a tangent at 0.3. So I just need to draw a tangent at this point. I will attempt at doing that the best I can, but obviously use a ruler, pencil, make sure that the tangent is as accurate as you can make it, and then find the gradient of that tangent. Always also just extend the line as much as you can to take as much of the graph as possible, and then draw a triangle in to show the examiner that you are working with a very large triangle to get the change in x and the change in y. Now if you do that, if you do the change in x and over change in y in this graph, you should get 2 times 10 to the minus 5 for the electric field strength. Sorry, not 2 times 10 to the 5, my mistake, it's 2 times 10 to the power of 6. Okay, and electric field strength can be measured in volts per meter. You can see that from voltage divided by distance, or since E is generally defined as a force per unit charge, it can be written as newtons per coulomb. Okay. They do accept a range in answers just in case your gradient isn't exactly 2, and they say plus or minus 0.3 for this value, so it could be 2.3 or maybe 1.7 times 10 to the power of 6. For this question we are asked to work out or to show that the capacitance is approximately 1 times 10 to the 11. Now, since it's one of those show that questions and they've got an approximate value, you want to use your answer to at least 2 significant figures when you do work it out. If I think about an equation that links capacitance with charge and potential, we've got C equals Q over V. Now, there are 2 ways of doing this. You could either just work out these values, so the charge at the sphere and the potential at the sphere. So remember, if I just draw this out, we've got the sphere, here's the distance from the center to the surface of the sphere, and this is the surface. So I just need the charge and V at surface. Okay, now we worked out that charge in the previous question to be 2 times 10 to the power of 6. And we also worked out, we can work out V from the graph at the surface. So if we go back and look at the graph, we can see, sorry, that was a mistake, that should be 2 times 10 to the minus 5 for the charge at the surface. And if we just talk about how we got that, we could get this value from the equation for the electric field strength is equal to Q over 4 pi E naught R squared, and we worked out E in the previous question, okay, to be 2 times 10 to the power of 6. R is, well, if you look at the diagram of the surface of that sphere, that's just the distance, which is the radius of the sphere, and you could get that number from the graph. So you can see that the radius of the sphere is 0.1, and it also says that in the question. So I just need to use 0.1 meters there, and if I just rearrange this to get Q, E times 4 pi E naught R squared, I could get the charge, which is equal to that number that I wrote here. Okay, so 2 times 10 to the minus 5 coulombs. So we have the charge, and then now we just need the potential at the surface. Coming back to the equation, sorry, not the equation, the graph. The potential at the surface, okay, over here, is 1.8 times 10 to the 6. So that's going to be, that value here is 1.8 times 10 to the power of 6. So putting these 2 numbers in, you should get a capacitance of 1.1 times 10 to the power of minus 11 farads. Okay, so alternatively, so another method you could do is by using this equation. So we know the potential is given by this equation. And if you look at this equation and the equation for capacitance up here, capacitance is Q over V. So I can make Q over V the subject of this formula, and that will give me 4 pi E naught R. And again, using R for the radius of the sphere, because we want to know the potential of the surface and the capacitance of this sphere. Putting these numbers in should also get you 1.1 times 10 to the minus 11 farads. Okay, so final question. Here we need to work out the energy stored, but actually just be careful, it says the change in energy stored in the sphere. So in other words, we need the energy stored. From this equation we can use a half CV squared, because I know the capacitance and I can get the potentials at these 2 instances. So at the beginning, when it's fully charged, we said that earlier that V equals 1.8 times 10 to the power of 6. Okay, and in this instance, so a bit later, V equals 1 times 10 to the power of 6. So if I could just work out the energy before and after and then just find the difference. So that's just a half C V squared at the beginning, so I'll just call that 1, V1, and I'll call this V2, minus a half C V2 squared, just to make this a bit simpler, half C V1 squared minus V2 squared. So again, as mentioned, the numbers here we worked out previously, 1.1 times 10 to the minus 11. V1 is written up here. V2 is up here. And then we can put the numbers in and get a change in energy to be 12.5 joules. You have to be careful about, using these numbers, because even if you didn't actually get the 1.1 times 10 to the minus 11, you could still use the number they gave you, and the error would be carried forward and they will still get you the marks as long as you use the right method. Question 4, we have some gravitational field lines around 2 stars G and H. The first question, we have to compare with reference to this diagram the masses of G compared to H. Now you have to be careful when you're answering this. We can see there's more field lines coming out of G than there is H, but it's not enough in the mark scheme if you look at to say that there's just more field lines in G, therefore it has a bigger mass. First of all, you do need to relate to the field lines, so we say density of field lines relate to mass, and we can see that G has a greater density of field lines, so it has a larger mass. For question 4.2, we have to show on the diagram the direction, field direction at x and the field direction at y. So we know the field lines in general show the direction of force. These are gravitational forces, so they should be pointing towards the object. So at x you'd have to draw a straight line arrow going towards G, and at y straight line arrow going towards H. This is a straightforward 1 mark question talking about gravitational field strength, so we write the equation for gravitational field strength, and since it's asking us to find the radius of P, so like we've been given the mass and the field strength at the surface, so therefore we're trying to find R from this equation. Rearranged, it should be equal to square root of Gm over G, and we've been given all the numbers here, and just find from the formula sheet the value of this universal gravitational constant. You do that and you should get an answer for the radius of this asteroid to be 1.8 times 10 to the 5 meters. Now in this one we have to sketch the variation of this field strength with distance, but be careful on the x-axis they actually start at the surface of the planet. So here's a planet, from the center to the surface is R, and then they want us to know what is at 2R and then 3R. So we're just multiplying the radius by a factor of 2 and then 3. Looking at the equation, we know that this is what determines field strength, and since G and M are constant for every position here, then it's just G is proportional to 1 over R squared. So for example, if I times R by 2, I have to divide G by 4 because it's an inverse square relationship. If I times R by 3 for 3R, then G would be divided by 9. So you can mark the points on the graph for the value of G at each of these distances. In the previous question we worked out G to be 0.4 at R, and at 2R it will be a quarter of that, so we're at 0.1, and then at 3R is a ninth of that value of 0.4, so that we divide that by 9 we get around 0.04, and then you just have to kind of join this up. Ideally use a solid line when you're doing this. It's just easier for me to do dashed lines here. 4.5 is asking us to look at a feature of the graph, which is the area. So whenever you see graph questions, just look at the labels on the y and x axes and find an equation that links the two. And you can see the equation, the formula sheet for G is delta V over delta R. So if you look at what area represents, this area here, area is just whatever's on the x-axis times the y-axis. So that's G times delta R, and that should be equal to delta V. So you have to write in words that area is the change in gravitational potential, and then specifically for the 2 marks you have to add that to move from R to R. So going from, like, say, this position here on the surface, moving it to this position, and we know there is an increase in potential as you move away from the surface. So there is an increase, we should also add to be more clear. Okay. This final question looks quite tricky looking at the diagram, but if you would just break it down and think about forces acting on the asteroid, because they say that there are two forces. There's a force acting due to G, I could call that F, due to G, and they told us that this is 6.38 times 10 to the 12 newtons. And there's also going to be a force due to H. Okay, so this asteroid is experiencing two forces, which are, by the way, right angles to each other. So that's important later. And we just need to work out this force. I call it F due to H. So the force between any two objects, use the gravitational force, Newton's law of gravitation equation, G m1 m2 over r squared. In this case, m1 is the mass of P, the asteroid, and m2 I can use as the mass of H. Put into this equation, and they have given us r here as well, so we just put this into the equation and we get the force due to H to be 1.8 times 10 to the power of 13 newtons. Okay, so I have the force due to H, I have the force due to G. They're right angles to each other, so we have to use Pythagoras here to find the net force. Okay, and that's just, the force of H squared plus the force due to G squared, all square rooted. So I've got these numbers now. Here's the force of H, here's the force of G. Put into the equation and you get the net force to be 1.9 times 10 to the power of 13 newtons. So in the question is asking us to find the acceleration of P, so we could then finally use the F equals ma equation to get A, which is the force, the net force on P, divided by the mass of P. So this net force, which we worked out here, divided by the mass of P, which was given to us at the beginning over here, and we should get the acceleration to be 9.5 times 10 to the minus 8 meters per second squared. Final question here. We are asked to explain why P cannot have a circular orbit around H. So here's P, and we're saying why can't it have a circular orbit around H? Now, if you remember your conditions for circular motions, we should add this. So for circular motion, the net force, which we call the centripetal force, must act towards the center of the circular path that is made. In this case, H, that's the direction that the net force should point. Okay, so net force should point in the way I've just drawn this arrow here, but we know that can't be true because there's another force acting towards G, so it's not gonna, the resultant is not going to point that way. If we look at our tip to tail method, for example, the resultant force is going to be more like pointing in this direction. Okay, so that's not acting towards H. H was over here, P was over there, and therefore, the net force is not acting towards H. So not in circular motion, because net force not pointing towards H. Question 5, we have a transformer, and in this question we have to explain the function of the core and the secondary coil. Now, if you remember about transformers, we have a AC, alternating current voltage, in the primary coil, and that's causing a change in flux. Now that change in flux will get transferred over to the secondary coil even if that core is not there, just from the fact that we know that a current through a wire causes a magnetic field. Changing magnetic field will be then induced in the secondary coil. But what the purpose of the core is to actually increase, so it increases the magnetic flux linkage from primary to secondary coil. The purpose of the secondary coil, first of all, again going back to understanding that it will have a changing flux through it. So the changing flux will, as we know, induce an EMF according to Faraday's law of induction. So the changing flux will induce an EMF, and due to the greater number of field turns in the coil, it will be a greater EMF induced. Right, so this question we have to recall some of our knowledge about how the efficiency of a transformer is improved, is increased, looking at the design of that core specifically. So in this diagram you can see that there are layers. So it's not one solid block of iron, there are layers, so that will be one of the reasons. So we need two here, so to get the 3 marks we need to get 2 reasons and the reason why it improves. One of the reasons to be able to always recall for transformers and efficiency is that the core is laminated with an insulating material. This is to limit eddy currents. So we don't want currents to go through this iron core, we want to limit the amount of eddy currents that are in the core. The other reason is this thin sheets of layers. So thin sheets of laminated iron will also reduce induced EMF in the core. Okay, we don't want EMF to be induced in the core, we want it to be transmitted to the secondary coil from the primary coil. In this question there are reasons why high voltages are used in power transmissions, but what's often missed is that there is a limit to that voltage. You can't have it, to really, really high, like millions of volts. So the first mark comes from our usual sort of understanding of high voltages. This goes back to what you might have learned from GCSE. So high voltages are used to limit the current, and so heating loss in wires. Okay, so the larger the current in wires, the more loss due to resistive heating. But too high voltage means more expensive insulation is required. So they need to come to a compromise when it comes to the size of the voltage in the transmission lines. This final question, we have to think about the current in the 25 kilovolt line of the power station. So this is the very first transmission line, this 25 kilovolt line over here. And so there's a power that is coming from the power station here. And as it goes through each of these points, so like this transformer here, when it gets through the transformer, it says in the question that the transformer has an efficiency of 98%. So the power actually goes down by this much. So whatever the initial power was here, it becomes times 0.98 when it goes through this first transformer. It also says in the question that the transmission line itself has an efficiency of 94%. So as it goes through this transmission line, P decreases by, actually let me just get rid of that P here so it's not confusing. So what we're saying is that each of these stages will cause a decrease in the power. So that decrease, we need to know, is by those percentage amounts said in the question. Okay, so if I just add this in here, we mean times 0.94. And then again, one more time in this transformer is times 0.98 again. Before it gets to the consumer, value of P equals, it says here 72 megawatt power is what the industrial consumers actually get. Okay, so if I just write this out as an equation, so we say that the initial power coming from the power station altogether is multiplied by 0.98 times 0.94 times 0.98 again. So times 0.98 times 0.98 times 0.94, and that's equal to 72 megawatts. So if I rearrange this, I could get the initial power output of this power station here to be roughly, if I were to do three significant figures, 79.8 megawatts. Okay, so this is the power output from the power station, and then that is the power being transmitted through this 25 kilovolt line, and that's what it's asking us to work out what the current is in the 25 kilovolt line. So we know P equals IV. I could use this equation. So I do P divided by V equals I. So this 79.8 times 10 to the 6, because it's megawatt, divided by 25 times 10 to the 3, 25 kilovolts. And you get 3190 amps, 3190 amps. Question 6, there are two ways to answer this first part, definition for the binding energy. You can either say it's the energy required to separate the nucleus into its individual nucleons. Okay, so that's fine, that's the definition. Otherwise you could also say as the energy released when the nucleus is formed from the individual nucleons. It's important to say the individual nucleons rather than just saying the energy required to separate the nucleus. This next question is to calculate the binding energy for a nucleus of iron. So in the previous answer we said that there is a change in energy here. So the idea that the individual nucleons that make up iron will have a different mass to the nucleons when they're joined to form the nucleus. So there is a change in mass, or we call the mass defect, which is taken from by doing the mass of nucleons minus the mass of the nucleus. Okay, they've given us the mass of the nucleus in kilograms. We just need to find the mass of the nucleons. So using a data sheet, look for the mass of the proton, which is given as 1.673 times 10 to the minus 27 kilograms, and the mass of a neutron is given as 1.675 times 10 to the minus 27 kilograms. It's important with these binding energy type calculations always to use as many as 4 or 5 significant figures where possible when you're doing the calculation and carrying the numbers forward as well to the final answer. So if I do this calculation for the mass of the nucleus, which is 9.288 times 10 to the minus 26, take away by the mass of the individual nucleons, using the mass of the proton, mass of the neutron from the data sheet. So if I just add this bit in here, mass of the nucleons is 26 times the mass of the protons, plus 30 neutrons times the mass of the neutron. And then subtract from this mass, and you get a mass defect, a mass difference of 8.68 times 10 to the minus 28 kilograms. So to now work out the binding energy from this mass difference, we use E equals delta m c squared, and again, data sheet for C, 3 times 10 to the 8, you should get energy in joules to be 7.812 times 10 to the minus 11 joules. So that is the binding energy in joules, but the question wants you to write this answer in MeV, so just do your conversions as from joules to MeV by dividing by 1.6 times 10 to the minus 19 to get it into EV, and then divide it by 10 to the 6 to get into MeV. And when you do that, you get a answer of 488 mega electron volts. This is a bit of an unusual question because you have to, there are quite a different range of possible answers here, but you have to follow a certain set of rules for these answers, and then quite a few possibilities are accepted in the mark scheme. So first of all, understanding that in fission, or even in fusion, that process involves splitting of nucleus into two smaller nuclei. Okay. The second thing to point out from fission is that if you look at this graph, we have the binding energy per nucleon curve, and for both fission and fusion, so in this case X is going to undergo fission, it should move to the left, and we must have the total binding energy per nucleon for each of the two nuclei that formed has to be larger than X. So the nuclei must have a binding energy per nucleon greater than X. Now, looking at this, it does limit us to a range of numbers, but as long as it's to the right of this peak, so here's the peak, it's at 50, as long as one of the nuclei to the right of the peak, then that's fine. And you have to also make sure that the nucleon numbers, they both, whichever one you pick for F1 and F2, have to add up back to the nucleon number for X. So looking at this, I'm going to say it's roughly 240 as a nucleon number. So for example, if I picked, say, somewhere around here, 75 for F1, then F2 has to be around 165. Okay, so 165 being roughly around here. But I'm going to pick a number that's here for 100, so F1 could be maybe here, and then F2 needs to be a nuclear number that then adds to 100 to make 240, so we need around 140. So 140 is about here for F2, and that should be fine. The final question here, we need to understand that when large nuclei do undergo fission like this one, the resulting nuclei still are quite large in terms of their size, and fission fragments are usually much higher in their content of neutrons compared to protons. So fission fragments are large nuclei with a high NZ ratio. Okay, so remember N neutron number to proton number. It's not enough just to say it has a large number of neutrons. You have to say that it's, compared to protons, it has more neutrons. So a large number of neutrons compared to protons, or just an NZ ratio. So therefore, for example, if I was thinking of my nuclei that was 100, that would be, say, a proton number of 40 and a neutron number of 60. Okay, which does place it above the stability line. So above stability line, and usually if you're trying to get to the stability line, you need to reduce the number of neutrons. So this is trying to go towards the stability line. So a neutron turns into a proton, and that is beta minus decay. For question 7, we have to look at the ideal gas equation, and it's one of those questions where you have to look at what's remained constant due to a change, and they've given us like a temperature of this gas, and they've told us that the pressure also remains constant because it's restored to its initial value. So compared to how it was before and after, the pressure hasn't changed. We're going to assume it's a fixed mass of gas. No gas can leave or enter, so we're going to assume the number of moles of gas is the same. R is also a constant. So if I just take all the constants that I've just underlined here to one side and everything that is changing to the other side, then I get V over T is equal to nR over P, which is constant. So once you have the equation where you have the changing terms on one side, you could write an equation with the initial and final values. So V1 over T1 is equal to V2 over T2. Okay, so we have the initial temperature 300, we're trying to find the final temperature, and they have told us about the volume and how it's changed. So the volume is compressed to half its original value. So in other words, the initial volume is twice the new volume, V2, and I could just substitute that in for V1. So if I look at V1, that's the same as saying 2V2. Okay, so V2's cancel. T1 was 300 Kelvin. I could rearrange this equation now. 2 over 300 equals 1 over T2 to get the new temperature to be 150 Kelvin. Okay, so it's A. In question 8, we are given a fixed volume of gas, and again we need to look at the equations that link some of the options given in the in A, B, and C and D, and it's asking us to pick a row that will meet the condition where the temperature of the gas doubles. So we're thinking of what else will double if the temperature doubles. So just look at your formula sheet and find some of these equations. For example, I can see there's an example of density in it, so maybe we could have a look at that and see how density is affected by an increase in temperature. Well, we know density of anything, including a gas, is mass divided by volume. So it's a fixed volume of gas. So as it's heated, the volume hasn't changed, the amount of gas hasn't changed. So this is actually constant, even if you change the temperature. So we know it's not going to be row B or row C. So now we're left with looking at pressure, internal energy, and the root mean square speed of the molecules. So if you remember for an ideal gas, the total internal energy is made up of its total kinetic energy of the gas. So looking at the equation for kinetic energy, we see it's equal to 3 over 2 kT. There is also another equation that links this with volume and pressure. So first of all, in this equation I can see if I double the temperature, it will double the kinetic energy. Now and remember, this equation is just for one molecule. So for the whole gas, it will be n times that value. So EK for whole gas is equal to 3 over 2 n kT, like this, where n represents the total number of molecules. This is equal to a third nm CRMS squared, which is also equal to PV. Now if you look at all these equations now, you can see that there is a relationship between temperature, CRMS, and pressure, because volume is fixed, number of molecules I say is fixed, and mass of gas is fixed. So this is what I see as a relationship. Pressure is proportional to temperature, which is proportional to CRMS squared. So if I double the temperature, the pressure should also double. Okay, and remember, temperature is also related to the total internal energy or kinetic energy of the gas. So the only option that's true here, if you double the temperature, is pressure and internal energy of the gas. In this one, we have to look at the equation for gravitational field strength. Okay, and see that it's proportional to m over r squared. So for each of these options, it's telling us how m is changing. So if, for example, in row A, if you double the mass and double the radius of the planet, and we want to see which one of these will give us a value of 4 times the original gravitational field strength. So looking at option A, let me just write it here. So we have 2 times m divided by twice the radius, which is squared, and therefore that will just give us 0.5 overall, a factor of 0.5. So that can't be correct, because I want 4. This one as well, if you look, it's like the mass is half and radius is √2 squared. And again, that doesn't give us 4, a factor of 4, that only gives us a factor of a quarter, 0.25. And you could try it with the other one, but the final one that will actually give you 4g is this one, because we have, again, 2 times the mass divided by 1 over √2 squared. And if you did this in your calculator, you get a factor of 4, which is what we want, 4g. So it's going to be D. Okay, question 10, we need to work out the angular speed of the moon's orbit. So angular speed is omega is 2 pi over t. So quite a straightforward question here. We just need to convert this time into seconds. Okay, so you do 2 pi over 27 times 24 hours in the day times 60 times 60 to get it all into seconds. And put that in your calculator and you should get the answer to be to 2 significant figures. This one B, 2.7 times 10 to the minus 6 radians per second. Question 11, we need to get the equation for escape velocity. Now you can just recall, it's a good equation just to know and recall that the escape velocity is given by √2 gm over r. And even if you can't recall that, there is a way to get this equation by thinking about equating the potential energy gained from the initial kinetic energy to leave any gravitational field. Potential energy in the equation sheet is gm over r. Kinetic energy is half mv squared. So the m, the object, cancels with the m here, and I could just rearrange this equation to get v squared, or just v. Actually, let's do this in one go. V is again 2gm over r. Now that doesn't match with any of the options, but you can see in all the options they've given you g, and if you remember, g as an equation is gm over r squared. And then if I just rearrange this slightly to write like this instead, so multiply both sides by r, I get gm over r. The reason why is because this term is already here in escape velocity. So in other words, I could just replace that gm over r with just gr. So v escape is equal to square root 2gr. Okay, so that should just be B as the answer. In this question, we have to think about an equation that links period of rotation in gravitational fields. Anything to do with time period, velocity, like orbital quantities, we want to always link in circular motion with the type of force in question. So in this case, gravitational forces. So gravitational force is gm over r squared, and centripetal force that is causing this gravitational force is omega squared r. You could use mv squared over r, but I'm going to use omega because I'm trying to get time period, and I know omega is equal to 2 pi over t. So I might need to make that substitution at some point. So looking at this, I can cancel the m's. I can divide both sides by r, and I get omega equals the square root of gm over r cubed. And since omega is 2 pi over t is equal to all of this, gm over r cubed. I just need to rearrange this now to get t equals. Quick way to do it, just flip both sides here and multiply by 2 pi. I get t equals square root of r cubed over gm times 2 pi. And the one that matches with that is C. For question 13, we have to think about what one of these quantities will be smaller for n than f for these two satellites in a circular orbit around the same planet. Order or radius of n is less than f. So if I just do a quick sketch here, radius of the planet, let's say n is here and f is a little bit further away. Okay, it just helps visualize these kind of quantities. For each of these, let's think about which is smaller. So which is smaller for n. It can't be gravitational force because we know for gravitational forces F equals gm over r squared. So n is closer to the planet, so r is smaller, therefore f is going to be bigger. They both have the same mass, so it can't be this one. Excuse me. For B, speed of the satellite. Now, the closer a satellite is to a planet, the faster it is. But I mean, if you wanted to prove that and show how that's true, you could equate centripetal acceleration with gravitational acceleration, gm over r squared. And when you rearrange this, you see v squared is equal to gm over r. So the smaller the orbital radius, the bigger the velocity. Okay, so n is not going to have a smaller speed. It has a smaller radius, so it has a bigger speed. And for that same reason, it can't be this either, because we know kinetic energy is also proportional to v squared. Okay, so since we've said v is bigger, EK is also bigger, kinetic energy. So that does leave us with D as the answer, but again, you could use the equation we just done earlier, this one up here, to show that to be true. The smaller the radius of the orbit, n has a smaller radius of orbit, then the smaller its time period. In question 14, we have to look at equating, again, a circular motion equation, in this case, involving magnetic fields. So if we look at the equation sheet for the force on a moving charge is BQV, and we equate that with circular motion, centripetal force, because that is causing resulting in circular motion, so mv squared over r equals BQV. Cancel the v's, well, not the v's, just v on one side, and rearrange to get r equals to see how the radius is affected. So r is equal to mv over bq. Now, all we've got to do now is just look at the question and see, well, what has changed in this new situation. The second electron, so therefore it has the same charge, that's constant, in a field that is 4 times greater, so times 4. The speed is 0.5 times the speed, and since it's an electron as well, so the mass is also constant for this electron. So in other words, I could just see that what I'm left with is 0.5 on the numerator and 4 on the denominator. So that gives us a radius of an 1/8 of the original value, and therefore it's A as the answer. Okay. Now in 15 we have to think about another energy equivalent energy transfer that's taking place here. A charged particle with charge q is accelerated through a potential difference, so electrical energy is being converted into kinetic energy for this charged particle. So I need to equate those two energy equations. Electrical energy is QV, kinetic energy is half mv squared. So these two v's are different, that's just potential. I'll use capital V, and lowercase v is the velocity. In fact, I'm just going to use u, because in all the options I can see that they're using u here for the speed, and it says u here as well. So I'll just use u in this case. I need to get this equation to get v equals. So if I start rearranging, I see that v squared equals 2qv over m. And again, just looking at what's changed, the charge is now times 2. The potential here, that should be u. The potential here is times 2 as well, and the mass is 0.5. So what I'm left with is 2 times 2 on the numerator divided by 0.5, and that gives me 8. So u squared goes up by a factor of 8. Okay, so that means if I square root, u goes up by a factor of root 8. That's the same if you just do root 8 in your calculator, it should give it to you in the form of the same as 2 root 2. Okay, so that means it's B as the answer. For the next question here, question 16, this one was a bit tricky at first for me, because I just got confused by these field lines, thinking that's the direction of the potential. But I think with any field lines, it does help to just draw in what causes it. This is a parallel set of lines, a uniform electric field, and we know that's caused by 2 parallel plates. So if I just add this in and just draw in 2 parallel plates like this, field lines are going from left to right, so that means this plate must be positive and this plate is negative. Okay. So in other words, potential goes from left to right, or right to left if you want to look at it that way. And if I want to move through the potential, I need to go in the direction that I see these arrows. That's moving through the potential, or forces required to move through that potential. In this question, we want to work out the total change in electrical potential energy for this charge to move from R to T, so moving in this direction. Now, there is no change in potential perpendicular to this field, so I don't need to consider this 4 meters. The only displacement that's important in this change in potential calculation is the horizontal displacement, so this displacement here along the direction of the field, and that's only 3 meters. So the displacement here is 3 meters. So to work out the energy, again, electrical energy is given by QV, okay, where the V, the potential, is found from the electric field strength in a uniform field, which is V over D. So V is equal to E times D. So I can use this in this equation to write it as Q times E D. Okay, let's put the numbers in now. So 3 times 10 to the minus 6 for the charge, times the electric field strength, which they told us to be 15 volts per meter, times the displacement along that field, which is just 3 meters. And doing that, it gives you 135 micro. So it's going to be A as the answer. Question 17, we have to look at this capacitor circuit and decide 2 things. First of all, the direction of current when the capacitor is connected to the ammeter, and then finally the size of that current. Again, we can eliminate 2 answers quite easily here just by thinking about the direction of current. So in a battery, this is the positive end, that's the negative end. When it charges, electrons move around the circuit, it leaves this plate positive and that plate negative. So that means in this circuit, that plate is positive, that plate is negative. We know current goes around from positive to negative. So that means it's going to go from X to Y. That means I can eliminate B and D. Now to get the current is given by the equation I equals Q over T. And I have to think about what the charge is, and that's been can be found by looking at the equation with capacitance and voltage. So from the capacitance equations, we know that charge is equal to CV. So therefore, the current is, I replace Q with CV and then divided by T. So all that's left to find now is this time taken for the charge, or the discharge in this case. And it told us here there's 8,000 charge-discharge cycles every second. So 8,000 in a second, that means one discharge must be 1 over 8,000. So this is 1 over 8,000 as a time in seconds. The voltage or potential difference across the capacitor once it's fully charged is 4 volts, and the capacitance is 0.4 microfarads, so that 10 to the minus 6. You put these numbers in and you get 1.28 times 10 to the minus 2 amps, so that matches with A as the answer. For question 18, we have to look at some of our equations for capacitors, the time constant, discharging, and we can eliminate some of these answers, but just by looking at a few to begin with. So we've been given the resistance and we've been given capacitance, so we could get the time constant straight away. Time constant is equal to RC. You put these numbers in, 30 microfarads times 500 kilo ohms, making sure you deal with the prefixes here, and you get a time constant of 15 seconds. So A can't be correct, that's 15 milliseconds. Initial charge, well, I could use the capacitance equation for charge and voltage, so Q is CV. Again, using the values for C, 30 microfarads, V in this case is 4 volts. That gives us a initial charge of 12 times 10 to the minus 5, not 12 times 10 to the minus 6 as option B has said, so it can't be B. We can look at why C is the answer, because if we want to know how much voltage is remaining after a period of T, which is the time constant, look at the equation, V equals V naught e to the minus lambda T. That's the wrong equation. That should say T over RC. I'm confusing that with the decay equations here now, so let me just correct that. Okay, so the decay, not the decay equation, the capacitor discharge equation is T over RC. So it says a time period of T later, which is the same as the time constant, which means that this whole term becomes T over T, or RC over RC. Okay, it's just 1, so that means V naught e to the minus 1, where the initial voltage they told us is 4 volts. 4 e to the minus 1, and that does give you 1.5 volts, so C is the answer. The reason why D is not the answer in this value they've given us here, it should have been Q naught e to the minus 2. You could do the similar kind of calculation here with the equation Q equals Q naught e to the minus T over RC again, and just see that that's true. For question 19, we have to look at the equation for the capacitance of any capacitor based on its dimensions. So that's C equals A E naught ER over D from the formula sheet. And they told us in this question that the permittivity, relative permittivity is a third, so that's 0.3 recurring. The separation is also a third, so that's 0.3 recurring again. And it's a square plate size 3L, so that means new area is 3L times 3L, or in other words 9L squared, where the original one was just L squared. So that means this area has gone up by a factor of 9. So just looking at this, we're left with 9 times a third divided by a third, or that just cancels, and we're left with an increase in times 9. Okay, so C has to be the answer here. Question 20, capacitor is connected across the battery. The important point for this question is that it's not being disconnected. So the capacitor is in continuous connection with this battery, which means the voltage across it is constant. Okay, so that can't change. So we want to work out the new energy stored as the separation of the plates is halved. So there are 3 different equations you can use for energy stored in a capacitor. This is the most appropriate to use because I know V is constant, which means E is just proportional to whatever the capacitance is. And we know that changing the distance between the capacitance changes the capacitance because of this equation, E naught ER over D. So you can see that, well, if you keep everything else on the top constant, then C is proportional to 1 over D. So if you half that, then this multiplies by 2. So in other words, in this equation here, this multiplies by 2, therefore this multiplies by 2. So C is the answer. Question 21, we need to look at getting a few of the equations to work out how much charge or voltage might be stored in this capacitor after 1 minute. So one thing we can work out straight away from capacitance and resistance when you discharge a capacitor through a resistor is, so this is the capacitor, that's the resistor, is the time constant is R times C. You could use these numbers, 15 kiloohms and 2 millifarads, to get a time constant of 30 seconds. So that's going to be important when we look at the equation and see, well, how much charge, for example, might remain after 1 minute. So we know the equation for discharging is Q equals Q naught e to the minus T over RC. So after 1 minute, T here is 60 seconds. Now if I want to write this as a fraction of the initial charge, Q over Q naught, remember Q naught is the initial charge and Q is whatever is remaining after some time. So this is the fraction of how much charge remains after a certain amount of time. And the time I want is, well, the time here is 1 minute, which is 60 seconds, divided by the time constant, which is 30 seconds. So in other words, the fraction that remains is e to the minus 2. Now we also know that energy, again, is equal to half Q V, or if I just use the equation where I have a constant, then I'm going to use the Q squared over C equation because I know the capacitance is constant. So in other words, E is proportional to Q squared. So since I know the fraction of charge remaining is e to the minus 2, if I square that factor, so e to the minus 2 squared, will tell me what the ratio of, or the fraction of the energy is stored. That's just e to the minus 4. E to the minus 4 is the same as 1 over e to the power of 4, and therefore D is the answer. Question 22, we have to think about forces acting on this wire, which is in equilibrium. So here's a wire. Imagine I'm just drawing forces acting on it. There's a weight downwards, and it's being supported by a magnetic field. So therefore, the force on a wire is given by BIL. I equate the equations because it's in equilibrium. The forces must be equal in size, and therefore B is equal to mg over I times L. They've given us the mass of the wire. G is just 9.8. I is the current, which is given to us here as well, 3 amps, and the length of the wire is 0.25. You put these numbers in and you get a flux density of 0.039. So that matches with B as the answer. Question 23, we have to consider the equations for flux linkage and EMF. This is quite a tricky one. You have to think about these equations mathematically, really thinking about what will cause these to be maximum, because in both cases it's saying the maximum flux, so that's BAN cos omega t, is at time t1, and the EMF is maximum at time t2, and that's written as BAN omega sine omega t. Okay, these are just taken from the formula sheet. Now let's look at one at a time. If you look at this top equation, the only way that this could be max is when cos omega t is max, and that maximum value that any cosine can be is 1. So if I write this separately here, cos omega t1 is equal to 1, and we know for that to be true, the angle here must be 0 degrees. Okay, cos of 0 is 1, right? So therefore omega t1 equals 0, and therefore t1 equals 0. Now let's look at the second equation. Again, for EMF to be maximum, it means that this value has to be equal to 1. Maximum value that sine of anything can be 1. So again, I can write this out here like this. Omega t2 this time is equal to 1. And again, we know from our calculator, if it's on degree mode, you might remember this from GCSE, that 90 degrees is when sine of 90 is maximum of 1, when this angle here is 90 degrees. But these equations are for the angles in radians, so this is actually the same as saying pi over 2 radians, and therefore I could write that as omega t2 is equal to pi over 2. Now we know omega is also 2 pi over t in the equations, so I could just rewrite this again now with the value of omega, 2 pi over t. Cancel the pi's, and I'm left with t2 is equal to, if I just rearrange this, take the t to this side, divide by 2, is t over 4. And we know t is 1 over frequency, so therefore t2 can be written in terms of frequency as 1 over 4f. Finally, for this question is saying what is the smallest value of t1 over t2. Therefore, if I look at this equation, I have well, t1 was just 0 and t2 is 1 over 4f, so you're just left with 4f, 1 over 4f, sorry. Okay, so it has to be B as the answer. Okay. For question 24, we're looking at power dissipated in a electrical circuit. Now, since they've given us current and resistance, the power equation I'm going to use is, so initially P1 is equal to I squared R, so that's the initial power, I'm just going to call P1. In the second resistor 2R, the current has a peak value of I. So this is I naught in the equations in AC signals. And you should remember from circuits of AC, or alternating current circuits, the actual current delivery to the resistor is its root mean square value. So we need the root mean square current, which is equal to I naught over root 2 in the equations. So therefore, the second resistor, I call it the power P2, is going to be the root mean square current, I over root 2, because the initial peak current is just I, as given to us in the question. Okay, square it, because it's I squared R, and R is just 2R. Okay, I can just simplify this to write as P2 is equal to, if I just take out the I squared R separately, I'm left with the numbers 2 over square root 2 squared. So just 2 over square root 2 squared, I squared R. Okay, this just cancels. So you're left with P2 equals I squared R, which is the same as what P1 was. So that means it has the same power. B is the answer. In 25, this is just a recall question really. You have to remember the Rutherford scattering experiment and the conclusions of the Rutherford scattering experiment and the observations. The only thing that comes out from the Rutherford scattering experiment from these options is C. So C is the only correct one. That is a deduction from this, the observations made from Rutherford experiment. Question 26, we're thinking about alpha, beta, gamma radiation and seeing what of these statements might be true. So a little bit about alpha. Alpha is a helium nuclei, so it has a +2 charge. Beta is just a fast-moving electron, so it has a -1 charge, no mass. Gamma is not a particle, it's an electromagnetic wave, or you can think of it as photon, so it has no charge, no mass. Okay, so I could just write 0, 0 if I want. So looking at these options, what we remember from magnetic fields is that magnetic fields do affect moving charges, because moving charges have a magnetic field of their own, so therefore they'll be affected by magnetic field. So therefore, yes, alpha particle is affected by magnetic field, beta particle as well, they're both charged, and gamma particle is not affected by magnetic field. So it looks like row A is the actual correct row. You could talk about why the others aren't correct. So for example, this can't be correct because gamma is chargeless, so it can't be affected by electric field. Only things with charge can be affected by electric fields. Alpha has a positive charge, beta has a negative charge, so that statement is technically correct, but gamma has no charge, so this is not correct. All of these types of radiation come from the nucleus. Okay, so to say that alpha doesn't come from the nucleus is incorrect, gamma doesn't come from the nucleus is incorrect. Oh wait, this statement is saying outside the nucleus. So actually, this statement is correct, this statement is correct, but this statement is not correct. Question 27. In this one, we're thinking about half-lives and how much mass remains after a certain amount of time. So we have initially P, which has 200 grams, and Q, which is 100 grams initially, and the half-life for each of these have been given here. So for example, after 12 days, P actually undergoes 6 half-lives. Okay. And Q will undergo, well, after 12 days, each half-life is 4 days, so therefore that's 3 half-lives. So if we know how many half-lives they undergo, then we could just work out how much is left. So in other words, if P starts about 200 grams, I have to half it 6 times, or just 2 to the power of 6. Q starts off at 100 grams, and I have to half it 3 times, or 2 to the power of 3. That's how much is going to remain in grams for each one. So I have to just add these two up, these two numbers, and I'll get 15.625 grams. So that matches with C as the answer. Question 28, we have half-life that's been given us as 10 milliseconds. So T half equals 10 times 10 to the minus 3. And we want to get the decay constant. In the equation sheet, you can see that decay constant is ln2 divided by T half. So if I just put these numbers in to the calculator, I get a decay constant of roughly 69 seconds. Per second, sorry. That's the unit for decay constant. And in these options, the only one that is within that range is B. So B is saying between 10 and 100 seconds. Yeah, none of the others are in that range. So B is the answer. Question 29, we have a question that is actually to do with nuclear excited states. So you learn about how some nuclei, when they decay, they are in an excited state, or we call them as a metastable state. And these metastable states are just nuclei that are in an excited state. So they have energy levels, just like energy levels with atoms and electrons. And because they're in an excited state, they then therefore de-excite, and the difference in energy is an energy released in terms of in the form of a photon. And these excited states release gamma radiation. So the only one that's correct here is the existence of gamma radiation. That proves that nuclei can have energy levels and be in an excited state. So C is the answer. Question 30, it's saying which statement is not true. So we're looking at any statement that seems correct, and that can't be our answer. So gamma radiation is more penetrating than alpha and beta. That is true. so this one can't be the answer. The intensity is inversely proportional to the square, and that is also true because we learned from the inverse square law of gamma radiation, one of the required practicals. The intensity of gamma radiation follows an inverse square law, so this one can't be true. This one can't be the correct answer. Gamma radiation can be emitted with discrete frequency if we treat it as a photon from E equals hf, so this can't be the correct answer. So it leaves us D as the correct answer, and really to understand this, if something is exposed to radiation, like let's just say a piece of cloth is exposed to radiation, as long as the radioactive isotope itself, the physical particles itself, is not on the material, that material doesn't start emitting radiation. Now, that material was not radioactive to begin with whatever atoms it was made of, so it can't emit radiation. Okay, so D has to be correct. When it is absorbed, it makes the absorber radioactive. That statement is not true. Okay, so that means this is the correct answer. Final question then, question 31. We have to think about nuclear fission and just recall some of our knowledge around fission. So this, we're looking for the true statement. First one, moderator absorbs excess neutrons. Note the job of the moderator is to slow neutrons, so it doesn't absorb them. For B, it's saying a large number of neutrons are needed for a fission reaction. That's not true. Only 2 or 3 thermal neutrons are required. Okay, even if you have, say, 100 neutrons released and they aren't slow enough, you can't get fission to be induced. So just 2 or 3 thermal neutrons are needed. Slow neutrons are required for this induced fission. This statement is definitely true, so we need thermal neutrons or slow neutrons for induced fission. This statement is not true because the control rod actually absorbs and stops neutrons. So we're left with C as the answer.